Welcome to the Fresh Thinking School of Brain Science. Today, I will discuss neuroengineering, a branch of neuroscience. What is neuroengineering? Neuroengineering is a field where engineering and neuroscience meet. It involves designing technologies that interact directly with the nervous system, the brain, spinal cord, and nerves. Neuroengineering is not just a field, it is an interdisciplinary frontier that combines engineering principles with a deep understanding of how the nervous system, the brain, spinal cord, and nerves works. It is a revolutionary field merging engineering, neuroscience, and computer science. Its goal is to create innovative technologies and techniques that allow us to interact directly with the nervous system. This includes monitoring brain activity, understanding its complexities, and even designing treatments for neurological disorders. Neuroengineering promises to unravel the mysteries of the brain and restore lost function. As the lines between mind and technology fade, neuroengineers reshape our reality. Like programmers writing code for our biological computer, they pioneer treatments that could cure disease and expand human potential. But neuroengineering isn't merely about repairs. It is about unlocking a future where we transcend disabilities and augment our minds. With this power comes immense ethical responsibility. The wise use of these tools may be our era's greatest challenge. The ethical considerations in developing and using neuroengineering techniques are crucial and demand our utmost attention. Neuroengineers forge bridges across the divides of thought and action, ability and limitation. They provide the tools to navigate the boundless landscape of the mind. Neuroengineers are not just dreamers, they are creators of tangible solutions. They develop brain-computer interfaces that enable paralyzed individuals to control devices with their thoughts, a feat that was once the stuff of science fiction. They could also create advanced sensors to track real-time neural activity, shedding light on conditions like epilepsy. The potential applications of neuroengineering are vast, from restoring lost senses to developing treatments that directly modulate malfunctioning brain circuits, and pushing the boundaries of our interaction with the nervous system. Neuroengineering promises breakthroughs in understanding and improving human health. Neuroengineers create brain-computer interfaces, allowing people to control computers, prosthetics, or wheelchairs directly with their thoughts. They also design implants to restore lost senses, like hearing or sight, through artificial stimulation of neurons and develop advanced imaging tools to map brain activity in unprecedented detail. Neuroengineering is revolutionizing the treatment of neurological disorders like Parkinson's disease and epilepsy. It is also used to explore the fundamental workings of the brain, creating maps of neural activity that reveal how we process information and form memories. This rapidly growing field blends the principles of engineering and neuroscience to unlock new possibilities for enhancing human capabilities, aiding those with disabilities, and advancing our understanding of the brain. Applying engineering principles to build devices that can interact with or repair the nervous system. Neuroengineering is a field where engineers design tools and technologies that directly interact with our nervous system. The goal is to address significant neurological challenges. This includes repairing damage caused by conditions like stroke or spinal cord injuries. Neuroengineering and engineers work on restoring lost senses like sight and hearing or lost motor functions. Ultimately, they even aim to enhance the natural capabilities of our nervous system. Examples of their work include the following: brain-computer interfaces for controlling prosthetics, implants to reduce tremors, advanced brain mapping for improved treatments. There are 7 pillars of the neuroengineering. Neuroengineering has the power to transform the treatment of neurological diseases and injuries. It offers new solutions for conditions like paralysis, chronic pain, and sensory loss, bringing renewed hope to millions affected by these debilitating disorders. Neuroengineers could unlock treatment that restore function and significantly improve the quality of life. This could involve advanced prosthetics, targeted brain stimulation, or even regeneration of damaged neural tissue. The first pillar of neuroengineering is sensing and recording. Neuroengineering begins with the ability to see the brain in action. This requires specialized tools to monitor activity at different levels, from individual neurons to entire brain regions. Implantable electrodes offer the highest precision, recording the electrical chatter of individual neurons. These are used in research and the therapeutic technologies like deep brain stimulation, advanced imaging techniques like functional magnetic resonance imaging, fMRI, provide a non-invasive window into the brain. These tools visualize changes in blood flow, revealing which brain region become active during different tasks or mental states. Non-invasive methods like electrocephalography electivography, EEG, measure electrical activity from the scalp, offering a broader picture of brainwave patterns. These methods provide crucial insights for diagnosing disorders, understanding how the brain processes information, and potentially for real-time monitoring in brain-computer interfaces. The second pillar of neuroengineering is signal processing and analysis. Neuroengineering relies on a critical skill, deciphering the brain's language. Brain activity generates a torrent of complex signals akin to a symphony played in a foreign language. This is where computational methods step in. These methods act as translators, using sophisticated algorithms to analyze the raw data from brain scans or sensors worn on the head. They identify patterns, trends, and specific signatures within the data that hold meaning. Imagine extracting a clear melody from a noisy recording. That is the essence of this process. The extracted information becomes usable insights for doctors diagnosing neurological disorders or engineers creating brain-computer interfaces. For example, the data might reveal patterns like the epileptic seizures or activity related to specific thoughts, allowing devices to be controlled simply by mental commands. By unlocking the secrets hidden within the brain's signals, computational methods are essential for advancing neuroengineering and its potential to revolutionize how we understand and interact with the brain. The third pillar of neuroengineering is neural stimulation. Neuroengineering offers ways to directly influence brain activity using targeted, stimulated, and stimulation, a powerful tool for treating neurological disorders. This stimulation can take different forms depending on the desired outcome. Electrical stimulation can calm overactive regions of the brain, like putting a brake on runaway activity. This approach is used to suppress seizures in epilepsy. Similarly, deep brain stimulation involves implanting electrodes to deliver precise electrical impulses to deep brain structures, reducing tremors and improving movement in diseases like Parkinson's. Alternatively, stimulation can also boost activity in underactive brain areas. This might involve electrical stimulation to enhance specific brain functions or the delivery of carefully targeted chemicals. Researchers are investigating this approach to improve cognition and mood and potentially restore lost functions after brain injuries. The fourth pillar of neuroengineering is brain-computer interfaces. Brain-computer interfaces represents a frontier in neuroengineering, promising to break down the barriers between our minds and the external world. These systems establish a direct line of communication, allowing the brain to control devices or computers purely through thought. BCIs start by decoding brain signals. They analyze patterns of neural activity, representing intentions or commands, converting them into usable instructions that can operate a robotic arm or move a cursor on a screen. This grants a robust level of independence to individuals with paralysis or locked-in syndrome. The future of BCIs moves beyond control. Researchers explore ways to send information back into their brain. Imagine sensory restoration. Stimulating the brain's visual areas creates a rudimentary form of artificial sight. BCIs have the potential to unlock communication, restore lost senses, and fundamentally change our relationship with technology. The fifth pillar of neuroengineering is neuroprosthetics. Neuroprosthetics represents hope, bringing the gap created by lost sensory or motor abilities. These groundbreaking devices aim to restore function, providing a remarkable bridge between the brain's power and cutting-edge technology. Imagine a cochlear implant capable of bypassing damaged structures within the ear to deliver sound signals directly to the brain, restoring a sense of hearing for those living in silence. Or consider a prosthetic limb controlled directly by the user's thought, a fusion of neuroscience and neuroengineering that empowers those who have lost a limb. Neuroprosthetics are not merely replacements but extensions of the body, controlled by the same neural commands that once directed biological limbs or senses. This field has the potential to alleviate the challenges faced by those with disabilities, restoring not only function but also independence and a sense of wholeness. The sixth pillar of neuroengineering is neuromodulation. Neuromodulation offers innovative techniques to influence brain activity for therapeutic goals gently. Unlike direct electrical stimulation, these methods aim to nudge the brain into healthier patterns, promoting self-regulation and healing. One technique is transcranial magnetic stimulation, TMS, where magnetic fields are applied to the scalp, influencing the activity of specific brain regions. This is used to treat conditions like depression or chronic pain. Neurofeedback training involves showing individuals real-time displays of their brain activity, teaching them to control brainwave patterns linked to focus or anxiety consciously. Focused ultrasound is another imaging method allowing targeted delivery of sound waves to deep brain regions. This technology holds the potential for modulating activity without invasive surgery. By subtly shifting brain patterns, neuromodulation techniques open up exciting possibilities for treating a range of neurological and psychiatric disorders, potentially offering alternative or complementary treatment options for those who don't fully benefit from traditional approaches. The seventh pillar of neuroengineering is neuropharmacology. Neuropharmacology is the field where medicine and neuroscience meet. It focuses on how drugs interact with the nervous system, which includes the brain, spinal cord, and all the nerves throughout the body. Neuropharmacology is a field of science focused on how drugs interact with the nervous systems, the brain, the spinal cord, and nerves, and how they affect behavior. Neuropharmacologists investigate the specific mechanisms by which drugs influence the way neurons, nerve cells, communicate with each other. This knowledge is crucial for developing new medications and therapies for neurological and psychiatric disorders such as Parkinson's disease, depression, epilepsy, and chronic pain. By understanding the complex interaction between drugs and the nervous system, neuropharmacology plays a vital role in improving the lives of people suffering from a wide array of diseases and disorders. It drives innovation in the treatment of both physical and mental conditions. Neuropharmacologists design new medications to treat neurological and mental health disorders by targeting specific parts of the nervous system. They meticulously study how existing drugs work at a cellular level, unraveling the reasons behind their desired and potential side effects. This field also investigates how drugs change our behavior, feelings, and even our thinking processes. Neuropharmacologists can gain valuable insights into how the brain works under normal conditions by manipulating brain chemistry with medication. The ultimate goals of neuropharmacology are to develop safer, more effective treatments for the wide range of conditions affecting the nervous system. This research aims to improve the lives of those with neurological diseases, mental health struggles, and even addictions. Neuropharmacology is a branch of medical science that studies how drugs affect the nervous system. Neuroengineering extends beyond devices and technology. It also encompasses the creation of highly targeted medications for neurological and psychiatric conditions. Researchers in this domain delve into the intricate signaling pathways of the brain, identifying specific receptors and molecules involved in various disorders. Their goal is to develop drugs that act like keys, precisely fitting and activating or blocking these targets. This tailored approach aims to minimize side effects while maximizing the therapeutic benefit. Imagine a medication capable of silencing overacting brain regions in epilepsy or boosting specific neurotransmitters to improve mood in depression, all without broadly disrupting the brain's delicate balance. This precision approach in neuropharmacology offers hope for developing more effective and personalized treatments for a wide range of debilitating brain-based conditions. Neuroengineering is a transformative field with a potential to revolutionize how we interact with the world and even with our minds. By blending engineering tools with neuroscience insights, neuroengineers are unlocking unprecedented possibilities for understanding, restoring, and augmenting the brain's capabilities. Neuroengineers are creating a bridge between mind and machine through advanced neural interfaces. This has profound implications for individuals with disabilities, allowing them to control prosthetics or communicate directly through thought. Further down the road, such interfaces could enhance our cognitive and sensory abilities. Neuroengineering also offers cutting-edge tools for diagnosing and treating neurological disorders. Targeted stimulation, neuromodulation techniques, and sophisticated neuroprosthetics are changing the lives of those afflicted by conditions like Parkinson's disease, chronic pain, epilepsy, or paralysis. As the field progresses, ethical considerations around responsible use, inclusivity, and the impact of brain augmentation become increasingly important. Neuroengineers are uniquely positioned to shape the future where our brains interact with technology in new ways. Their work paves the way for a world where neurological conditions are effectively treated, disabilities are overcome, and perhaps our understanding of ourselves is transformed. Neuroengineering stands at the precipice of a revolution in understanding, healing, and potentially enhancing our brains. The ability to interface directly with the nervous system opens doors once confined to science fiction, restoring movement to the paralyzed, sight to the blind people, and hope to those with debilitating neurological conditions are profound goals within reach. Yet, profound ethical questions arise as we map the mind's vast territory and blur the line between human and machine. How do we ensure these technologies are accessible and equitable? Where do we draw the line between treatment and augmentation? Neuroengineering's future is thrilling, but it demands responsibility. The collaboration between engineers, neuroscientists, ethicists, And society is crucial to navigating this uncharted terrain. It is a journey with the potential to transform lives, but one that must be guided by both the boundless drive of innovation and a deep respect for the sanctity of the human mind. This is Dr. Masasikani Mishakosa, Director of the School of Brain Science, Fresh Thinking School of Brain Science. We thank you for coming around. Thank you.